The four single bonds that each carbon forms in alkanes with hydrogen atoms and with other carbons are formed by direct overlap of orbitals, forming sigma bonds. These bonds have high bond enthalpies, meaning they are strong and have low polarity, and as a result, alkanes are not very reactive. Alkanes will readily react with oxygen, however, when they burn. Low and medium chain alkanes are useful as fuels and can undergo incomplete combustion in situations where the oxygen supply is limited. There is a system you can follow to balance equations involving incomplete combustion. You start with the alkane and oxygen to make carbon monoxide and water. You first work out how many carbons are present and add this many molecules of carbon monoxide. In this case, 3 carbons in propane, so make 3 molecules of carbon monoxide. Then work out how many atoms of hydrogen there are in the alkane, and then add half as many water molecules. So we have 8 atoms of hydrogen in propane, so we need to add 4 molecules of water. Finally, add up how many oxygens you have in the products, and half this quantity and add this many O2 molecules. It doesn't matter if you have half quantities of oxygen. The carbon monoxide produced during incomplete combustion is toxic, and this is why, if you have gas appliances in the home, it is a good idea to have a carbon monoxide detector, since it has been named the silent killer. For complete combustion, the alkane must be burnt in a plentiful supply of oxygen. The combustion products from complete combustion are carbon dioxide and water. To balance a complete combustion equation, it is very similar to what we did with incomplete combustion. With propane, we have 3 atoms of carbon in propane, so we need 3 molecules of carbon dioxide. We have 8 atoms of hydrogen in our alkane, so we need half as many H2O molecules. Now we add up how many oxygens we need to react with the alkane. So we need a total of 6 plus 4, which equals 10, which means we need to add 5 molecules of O2. Alkanes will react with halogens in the presence of ultraviolet light to produce haloalkanes. You must learn about the mechanism of these radical substitution reactions. Mechanisms show the steps for how we believe a reaction takes place at a molecular level. When writing mechanisms, we draw curly arrows to show a movement of a pair of electrons. For example, when a bond breaks by heterolytic fission, we show the shared pair of electrons moving from the bond to one of the atoms to form a negatively charged ion. When bonds break by homolytic fission, the shared pair of bonded electrons are equally split, resulting in 2 species with a single unpaired electron, which we call radicals. When we want to show a single electron moving, we use an arrow with only half an arrowhead, which looks like a fishhook. The overall equation for the radical substitution of an alkane to form a haloalkane is as follows. We will now go through the mechanism to show the individual steps for how we believe this reaction takes place. The first step is the initiation step and involves the halogen, in this case chlorine, undergoing homolytic fission due to the presence of ultraviolet light to form 2 chlorine radicals. Radicals are very reactive. The next stage is the propagation stage, which are the 2 repeated steps that build up the chain reaction. This is the stage where the 2 products are formed as well as further radicals. The first propagation step involves the reaction of the alkane, in this case ethane, with the chlorine radical. One of the products, hydrogen chloride, is formed along with an alkyl radical. The next step involves the alkyl radical, formed in the previous step, reacting with chlorine to produce the other product, in this case chloroethane, and a further chlorine radical. The final stage is the termination stage, which, as the name suggests, brings the chain reaction to a close. This is when 2 radicals come together to form a molecule. From the chlorine and alkyl radicals we have made so far, there are 3 possibilities. 2 chlorine radicals can pair up to form a chlorine molecule. A chlorine radical and an alkyl radical can form a haloalkane. 2 alkyl radicals can come together and form a longer chain alkane. In this case, butane is produced. Radical reactions are difficult to control and will inevitably produce a plethora of products as well as the desired product.